Now let's do a slightly fancier example, and then we'll try to analyze the vector field, and hopefully this will make everything a little bit more tangible. So let's say that the velocity of the fluid or the particles in the fluid at any given point in the xy plane, let's say in the x direction, it is x squared minus 3x plus 2 in the x direction, plus y squared minus 3y plus 2 in the y direction. Make it simple so that we only have one thing to factor. So let's just do the math first. Let's figure out the divergence of our vector field. The divergence of our field, and I'm going to show you a graph of this field soon, so we'll get an intuition of what it actually looks like instead of my not so accurate drawings. So what's the divergence? We take the partial derivative of the x component with respect to x. So that's just, there's only an x variable here, so we don't even have to worry about keeping y or z constants. It's really just the derivative of this expression with respect to x. So it's 2x minus 3. And then we add that to the partial derivative of the y component, or the y function, with respect to y. There's only y's in the y component, so we just take the derivative with respect to y. So it's plus 2y minus 3. Or we could just say that the divergence of v at any point xy, so this is a function of x and y, is 2x plus 2y minus 3. Now before I show you the graph, let's analyze this function a little bit. First of all, let's just look at the original vector field and think about when is that vector field equal to when does that vector field have some interesting points? Well, I think some interesting points are when either the x or the y components are equal to 0. So when is the x component equal to 0? Well, if we factor the x component, that's the same thing as we could rewrite our vector field. If we just factored that, that's x minus 1 times x minus 2 I plus, and it's the same polynomial just with y for the y component. So y minus 1 times y minus 2 times j. So the x component is 0 when x is equal to 1. These are just the roots of this polynomial when x is equal to 1 or 2. Right? And the y component is 0 when y is equal to 1 or 2. And they're both equal to 0 if we have any combination of these points. So the points where they're both equal to 0 are 1, 1, x is 1, y is 2, right? Because then both components are 0. 2, 1, or 2, 2. So these are the points where the magnitude of the velocity of our fluid or the particles in the fluid are 0. And we'll see that in our graph in a second. And let me ask you another question. At what points are, well, let's first decide at what point is the divergence equal to 0? Let's say at what point is the divergence equal to 0? Let me clear up some space. I think I can delete this. We got our points. We figured out what coordinates are the magnitude of the vector field 0. So let's try to figure out when is the divergence equal to 0? So this is divergence. So if we set that equal to 0, 2x plus 2y, 2x plus 2y. Oh, sorry, you know what? This is 2x minus 3 plus 2y minus 3. So this is minus 6, right? Minus 3 minus 3, that's minus 6. That's my major flaw, adding and subtracting. Anyway, so the divergence, 2x plus 2y minus 6. And we want to know when does that equal 0. So let's set it equal to 0. And we could simplify this a little bit. We could divide both sides of the equation by 2, and you get x plus y minus 3 is equal to 0. You get x plus y is equal to 3. We could be finished there, or we could just put it in our traditional point mx plus b form. That's the way I find it easier to visualize a line. We could say y is equal to 3 minus x. So along this line, the divergence of the vector field v is equal to 0. Along the line, y is equal to 3 minus x. And if we're above that line, the divergence is going to be positive, right? Because if you just made this a greater than sign, that would carry over, and you'd have y is greater than 3 minus x. So y greater than 3 minus x, the divergence is positive. And y is less than 3 minus x, the divergence is negative. And you could just make this a less than sign and then solve, and you'll get y is less than 3 minus x if you want to know when the divergence is negative. So I think we've done all of the analyzing we can do. So let's take a look at the graph and see if it's consistent with our intuition of what a divergence is and the numbers we found. I hope you can see this. So this is the vector field. I don't have space to show it, but I think you remember this is, x squared minus 3x plus 2. This is the definition of our vector field. Have it graphed here. And we just figured out when the x components and the y components are equal to 0. And then we said, when are both of them equal to 0? And we said, oh, well, at the point 1, 1, well, this is the point 1, 1. And we see that the magnitudes of the vectors are 0 at that point. And actually, I could zoom in a little bit. Right around here, they're all pointing inwards, but they get smaller and smaller as we approach the point 1, 1, right? We also said at the point 1, 2, x is 1, y is 2. And here, too, we see that the magnitude of the vectors get very, very, very small. We could zoom in again. And we see the magnitude gets very small. The other points, 2, 1, once again, we see the magnitude gets small. And then 2, 2. So that's consistent with what we found out, that the vector field gets very small at that point. And then the other interesting thing, we said, okay, when does the divergence equal 0? Well, the divergence equals 0 along the line y is equal to 3 minus x. So the line y is equal to 3 minus x starts, the y-intercept is going to be 3, and it's going to come down like this. Right? So anything at any point on that line, the divergence is 0. And if we actually look at the graph, it makes sense, because I can't draw on this graph, but if we drew a circle right there, let's assume that that's on the line y is equal to 3 minus x, we would see that in a given amount of time, just as many particles are entering through the top right as leaving through the bottom left. Right? A lot are entering through the top right and a lot are leaving through the bottom left, and the vectors, though, are about the same. And if we go to the bottom, if we go here on the line, maybe there are, it looks like, maybe there are less entering, but there's also less leaving. I know it's hard to see, but anywhere along the line, you see just as much as entering as leaving, and that's why the divergence is 0. Now, let's look at some of the other points. So up here, we figured out the divergence is positive. And does that make sense? Let's pick an arbitrary point. If we were to draw a circle around here, we see the vectors on the left-hand side of that circle that you can't see because I can't draw on this graph. But let's just say this square. Let's say this square is my region, right? This one right here. If that square is my region, we see the vectors on the left-hand side are larger. The vectors leaving are larger than the vectors entering it, right? So if in a given amount of time, the more is leaving than entering, then I'm becoming less dense, or you could say that the particles are diverging, and that makes sense because I have a positive divergence. And if we go here where the divergence is negative, let's pick an arbitrary spot. Let's say this square right here. We see that the vectors entering it, the magnitude of the vectors entering it are larger than the magnitude of the vectors exiting it. So in any given amount of time, more is coming in than leaving. So it's getting denser, or it's converging. So a negative divergence, you can view it as getting denser, or it's actually converging. Actually, something interesting is happening at these 2 points. So we said that x is at the point 2, 1. We see that in the y direction, it's actually converging, right? If these above y is equal to 1, the arrows are pointing down, and below it the arrows are pointing up, right? So in the y direction, we're actually converging, or we have a negative divergence. Things are entering any given spot. But in the x direction, things are getting pushed out, right? So the reason why the divergence is 0 here is, though, you might have particles entering above and below a certain space, but you have just as many particles exiting through the left and the right. So it's kind of like particles are getting deflected out. So you, on a net basis between in both dimensions, you have no increase or decrease in density along that line y is equal to 3 minus x. And before I run out of time, I just want to give you that core intuition again of why the divergence is positive and why that means that things are flowing out when the rate of change is positive. So we said the divergence is positive. Let's say at this spot, right? So it makes sense. If our partial derivatives are positive, that means that the magnitude of our vector is getting larger and larger for larger values of our x's and y's, right? So if the magnitude of our vectors are getting larger and larger for larger values of x and y, the vectors on the right are going to have a larger magnitude than the vectors on the left. They're increasing in magnitude. And so if I were to draw a boundary, more is going to be coming out of the right than entering to the left, and so you have a positive divergence, or you're getting less dense. Anyway, I hope I haven't confused you too much, but I have run out of time once again. I'll see you in the next video.